Welcome back. In this video, we begin our discussion of contour curves. Remember when we were looking at a two-variable function in the form z equals f of xy, that we could graph this as a surface in R3. When we say the word surface, what we mean is a three-dimensional representation of a set of ordered triplets x, y, z that make this equation true. Usually we draw this on the three-dimensional axes and it physically looks like a surface. One of the things that is really cool about M1C is we can have multiple different ways to visualize the behaviors of functions in R3. An alternative way to visualize surfaces is known as plotting a contour graph. A contour graph, sometimes known as a contour map, associated with the two-variable function z equals f of xy, is a graph that displays many contour curves on the same axes. Notice that when we look at a contour graph, we're looking at a function which has two input variables and a real valued output, and that these graphs sit in R3. So they're very similar to the graphs of surfaces in the sense that when we actually go physically graph these things, we expect a three-dimensional object to come out. So the whole idea is that a contour graph plots contour curves, and if you're sharp and quick-witted, you might say to yourself, well, what's a contour curve? I'm so happy you asked. A contour curve for a two-variable function where we say z is equal to f of xy, we see that this is a two-variable function, and then we set a specific constant value in the range of our function, and we assume that this is given. A contour curve associated with the value z0 is a set of ordered triplets which you might read c of z0 of f. The contour curve associated with z0 of f is the set of ordered triplets x, y, z, such that f evaluated at input x, y is actually equal to z0. So here is the same thing in words. The set of ordered triplets x, y, z0 such that f evaluated at x, y is z0. And I wanted to make a specific call out. This contour curve associated with constant z0 is a subset of R3. It comes from intersecting the surface at z equals f of xy with the plane z equals z0. Do you remember what we called these in previous lessons when you intersect a surface with a plane? Ding, 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 ding. We called this the trace. Yeah. Contour curves are traces because they trace a path along the surface at which all points on that path have constant elevation. And in particular, the height of those paths, of that path, is at z0, the constant curve. I want you to think of this is a fun way to imagine this, is imagine you're on the side of a hill skiing, and instead of going down or up, you point your skis directly perpendicular to the steepest descent line, to the thing that goes down, and then you ski literally sideways along the hill. So here's a hill, here's you, and I'm going to go ahead and make an absolutely beautiful artist drawing. And then it looks like currently you're on a snowboard, so let me give you another ski there. And then literally you would be going along a contour map if you do not ascend or descend at all, but instead you stay at the same elevation or the same height. constant z naught. And you can see by that kind of silly diagram that I've just done here that I really should be doing in Mathematica, this is the intersection of that mountain that you're skiing on with a plane. You could ask yourself, well, why the heck are you going to introduce new nerdy notation, freaking nerd, with 5 different ways to say things, if this is just a trace? And I think that's a really good point. The thing that I'll say is, these traces are so popular that they get a special name. These show up in so many different fields. They show up in thermodynamics. They show up in meteorology. They show up in the optimization fields. I mean, you name it, these things show up in economics. I mean, they're all over the place. And so not always is it useful to look at planes in the XZ and YZ direction. These planes, these contour curves that come from intersecting planes parallel to the XY plane are such special traces that they get their own name. So that's the short way to think about this. All right, so the whole idea is that we have contour curves, which are set of ordered triplets associated with a constant height. What we can do now is actually take a look at an example of how to analyze contour curves, how to actually bring these. So to do this, let's take a look at the 2-variable function f of xy equal to 9 minus x squared divided by 4 minus y squared. We're going to want to get a sense of what the contour curves look like. So to do so, we're going to let z be in the range of f. Notice that the domain of f, x and y, the set of x and y, these can be any values because all we're doing is squaring them. There's no square root happening, there's no ln, there's no limits, these things aren't in the bottom. So we make a quick note that the domain of this function is indeed R2, and that's because polynomials are continuous functions on all of R, which means that we're going to take away from 9 squared values where we run through all possible values of x and y. And we can, I hope you can see pretty quickly that the range of this function is going to be the set of everything down to negative infinity all the way up to 9 touching 9. Because if you had x equals 0 and y equals 0, you would actually hit that local and absolute maximum. We'll learn how to find those using calculus later in this course. Okay, so we're going to set our z to be in this set. Z naught, you could call that. And then we're going to look at what happens if you set that to be constant. So here you would have 9 minus x squared divided by 4 minus y squared. Hopefully, if you consider this to be constant, you recognize the form of this particular equation. Do you recognize what type of object this is? Yeah, you got it. This is very similar to the general equation of an ellipse, but there are two things that are different. If I bring the x squared divided by 4 and the y squared over to this side, and then I bring the constant z naught over to the other side, we're almost to a place where we have the general equation for an ellipse. And I want to kind of remind you, just as a way to get excited about life and ellipses, that if I drop an a squared on the bottom here, a b squared on the bottom under y, and a 1, this thing would be an ellipse with x semi-axis length a, y semi-axis length b. We're almost there in the x, except this stupid 9 minus z naught is messing us up. So the question is, if we wanted to choose, really, one thing to do is just choose any z naught, right? Choose z naught to be 3. And then you'd have 9 minus 3, and then you'd figure out what this ellipse is. But my claim is these aren't going to be integer values. So we could do something kind of creative, which is to say, let's go ahead and introduce some notation, and we'll call this alpha squared. So we'll say that 9 minus z naught, can we find alphas so that we can think about this as a perfect square. And an example of this, let's look at our favorite perfect squares that are less than 9. Of course, we have our perfect square, I don't know. What are some perfect squares that are less than 9? I guess you have the perfect square 1. You've got the perfect square 4. And you've got the perfect square 9. So if you think about alpha squared as one of these, here we would have 3 choices of alpha, right? So we're going to write the output as a perfect square, and you'll see why I do this in a second. This would imply that alpha was equal to 1, or alpha is equal to 2 in the sense that it's 4, or alpha is equal to 3. And the really nice thing about doing this is we get some really, really beautiful equations out of this, right? If I divide both sides by alpha squared, I get back to my general ellipse formula. So this would be now 4 alpha squared plus y squared divided by alpha squared equal 1. And then of course here we would have this is x squared divided by 2 alpha quantity squared plus y squared divided by alpha squared equal 1. And here the x semi-axis would be 2 alpha, the y semi-axis would be alpha. And what's really fun about this is I can actually solve for these perfect squares. If I assume the output of this is a perfect square, that allows me to get a perfect square root, so to speak, an integer valued square root in the denominators here. And I can solve for what z must be, right? So let's go ahead and just run through the values of alpha. Let's start with the least interesting value, alpha equal 1, which would mean alpha squared equal 1, which would mean what? Well, we just said that we've assumed 9 minus z naught is equal to alpha squared, and then this would mean z naught is equal to 8. Okay? So if we take the contour curve associated with z naught equal 8, let's go ahead and look at what this is. Well, we said that that was going to be in our notation c sub 8 of the function f. This is going to be equal to the set of all x comma y comma z naught. This goes back to the definition that we covered in the first part of this video. And then the only claim was that 8 was equal to f of x comma y. Well, we've just seen right here exactly what that set is. So now you've got this is x comma y comma 8, and this is going to be 8 is equal to 9 minus x squared divided by 4 minus y squared. So we're trying to get this contour plot. So now this would look something like the set of ordered triplets x comma y comma 8. If I bring the 8 over this way and these over here, now I've got x squared divided by 4 plus y squared is equal to 1. Well, do you see what this is? Yeah, that's an ellipse in x and y at height a in the output. Right. I'll do one more for you, and then I'm going to let you do the last one for yourself. We will switch over to Mathematica to analyze this. Okay, so that was with our alpha. So this was associated with our alpha squared was equal to 1. Let's do the next version, which is a perfect square when alpha squared is equal to 4. Well, we know alpha squared equal to 4. We've just claimed that 9 minus z naught should be equal to alpha squared. That was by design, right? Because we were thinking the output as a perfect square. Okay, so this means that z naught, if I bring this over here and this over here, would be 5. All right, so now we have a contour plot associated, or contour curve, excuse me. Contour curve for z naught equal 5. This is going to be a different contour curve, right? So I'm going to have the contour curve associated with the height 5 of the function f is going to be the set of all ordered triplets x comma y comma 5 such that 5 is equal to 9 minus x squared divided by 4 minus y squared. Okay. And then we just saw that this is going to be the set of ordered triplets where the x and y trace out a ellipse. And what's really fun about this is we can now transform that ellipse into standard form where I bring these both on the bottom. So this is now x squared divided by 4 squared plus y squared divided by 2 squared equal 1. Okay. I'm going to let you viewers at home take care of the case when y squared is 9. When we do our Mathematica work, I'm going to assume that you've already done this, and we've now done 2 examples on how to do this. One note that I should make, let's pretend that I wanted to actually graph this thing, and I was going to do it as a contour plot. Excuse me. This is going to be a parametric plot, I think, because I want a curve in R3. So remember how we parameterized ellipses. We parameterized them by multiplying in the first component. We said this is going to be 4 times the cosine of t. In the second component, this would be the y semi-axis times the sine of t. And then since this is an R3, we're going to need a height. But the whole idea of a contour curve is that the height is held constant here. It's the height of the plane intersecting. So this, of course, would be 5. We could also go back and find, I don't know what you call this, maybe you call this R5. So this is the one associated with height 5. You could also go back and find the one associated with height 8, which we did previously. We saw that in that case, my x semi-axis would be 2. My y semi-axis would be 1. And the height along the surface would be 8. I'm going to make a claim for those of you that are following along at home. If you do this for alpha squared equal 9, this is going to get you a contour curve at height 0. And the semi-axis here would be something like, what is this, 2 times 3? So I guess that would be 6 times the cosine of t. And then this, of course, would be 3 times the sine of t. And the height associated with that one would be 0. These are the contour curves. They're curves in R3 that sit on the surface at the intersection of the z equals z naught planes. In the next video, we'll switch over to Mathematica and graph these contour curves. This will help us visualize how contour curves differ from just graphing a surface. See you in the next video.